In this video, we'll talk about the definite integral as a signed area. So I want to first recall that the definite integral, remember our definition was the integral from a to b, this represented our interval of our function f of x, and then I write dx, which is a notational thing. This equals this limit as n goes to infinity, the sum from I equals 1 to n, f of xi times delta x. And we use this limit of Riemann sums to express the exact area under a curve. So notice the similarities in how these are written. So when I have this Riemann sum limit, this f of x of I sort of becomes the f of x, the delta x becomes the dx. And then the a and the b, they were sort of underlying whatever interval we were finding the area over. Okay, so in the last video, I mentioned that this represents what's called a signed area. And that'll mean that when my graph is above the x-axis, I'll consider it as a positive area. But when it's below the x-axis, I'll count that as a negative area. So let's look at an example. All right, so we have this function. We have this straight line segment until I reach this point at 2, 6, where I have this upside down semicircle. And then again, another straight line segment extending to the right here. Okay, and I want to evaluate the integral from -3 to 6 of my function f of x dx. So if I look at my function over this interval, I'm going to draw this vertical line where x is -3. I'll draw a vertical line where x is 6. And I notice that there are a bunch of different sort of nice pieces to this area. So this region over here, I'm going to call this A1. And then I'm going to draw one more vertical line when x is 2. And then I'm going to call this next triangle, I'm going to call this one A2. And then we have this other shape, sort of to the right of that triangle, I'm going to call this region A3. So with those labels, my integral will count the area of this first triangle as a negative area. I'm going to write negative A1, because that region is below the x-axis. But the other areas will get counted as positive. So I'll have plus A2 plus A3. So we need to find these areas. So for A1, I'll have that negative sign in front, and then this is a triangle, so I'll get 1/2 base times height. The base of this triangle is 2. It goes from when x is -3 to when x is -1. So the base is 2, the height is 4. All right, for the next region, A2, again, another triangle, so I get plus this time, 1/2 base times height. It's positive because, again, this region is above the x-axis. The base of this triangle is 1, 2, 3, 3 units. And the height is going to be 6 units. And then finally, I need area 3. So I'm going to draw a picture of what that region looks like. We have this sort of shape, and then this semicircle. So what I'm going to do is I'm going to draw another line over here. Okay, because this sort of outer region creates a rectangle where the base of the rectangle is 4 and the height of the rectangle is 6. So what I'm going to do is I'm going to find the area of the rectangle and then subtract away the area of this semicircle, and that'll give me the area of the region I want, which is A3. Okay, so we will add the area of the rectangle and then subtract the area of the semicircle. I'll just write area of semi. Okay, so if I simplify these first areas, I'll get -4 and then plus 9. The area of the rectangle is going to be 4 times 6, length times width, and then minus area of a semicircle is 1/2 pi r squared, and the radius of that circle was 2. So we get 2 squared. Okay, so -4 plus 9 plus 24, that is going to be 27, because it's 5 plus, oh sorry, not 27, it'll be 29. Because it's 5 plus 24, that's going to be 29. And then I'll have minus 2 pi. And that's my answer. So that is what this integral is. As a signed area, it's 29 minus 2 pi. All right, let's look at another example. So in example 6, we want to evaluate the definite integral from 0 to 3 of the square root of 9 minus x squared dx. So let's try to graph this function. So we are going to try to graph it. Okay, so we may remember what the graph of something like this looks like from maybe algebra class, but let's just do a brief review. So I want to first recall that when I have something like x squared plus y squared equals r squared, this is a circle with center at the origin at 0, 0, and radius r. So with that in mind, I'm going to first graph x squared plus y squared equals 9. Because this is going to be a circle, I'm going to draw some axes. It's going to be a circle, and r squared is 9, which means the radius is going to be 3. So I'm going to go 3 units in each direction from the origin, and we'll get something like this, where this is 3, this is negative 3. So that's the graph of x squared plus y squared equals 9. All right, and now from this, I'm going to make it look more like my function by isolating the y. So I'll get y squared equals 9 minus x squared. And then if I square root both sides, we'll get y equals the square root of 9 minus x squared. But when I square root both sides, I got to put a plus or minus. Okay, so this is going to give me two possibilities. Either y is the positive root or y is the negative root. The negative root. Okay, and when I take the square root of something, the output will not be negative. It will be non-negative. That means with this equation, these y values are all non-negative, which means when I go to draw the graph, it's only going to give me the part of the circle that has y values that are non-negative. So that is just this upper semicircle. So where this is 3, this is negative 3, and that is 3. So that's that graph. On the flip side, if I had the negative square root, now that the negative's there, now these y values are not going to be positive. So this will be the bottom half. This will be the bottom half of the circle. Okay, so if we think about our integral is from 0 to 3. We now know the shape of our graph. It's this semicircle. But we just want it over the interval from 0 to 3. So that is just this part of the graph. So our integral from 0 to 3 of f of x dx, that's just going to be a quarter of a circle. So that's going to be 1/4 pi r squared. My radius here is 3. Okay, and working this out, this is 9 pi over 4. And that is our area. So I want to end this video by recapping the methods that we have at this point to compute a definite integral. The first way that we learned in this section was to use a Riemann sum. So to use a Riemann sum, but as we saw with these, this was very tedious, and it only really works well for low degree polynomials because we had to use our sigma notation formulas, but those sigma notation formulas, we only wrote them down for things like I to a power. So those will help for low degree polynomials. And as we saw in this video, another way to compute definite integrals was using areas. Sometimes I can just use geometry and figure it out directly using areas. But this only works if our shapes are simple. So e.g., for example, if they're linear or circular, it should be circular, if I have a linear or circular path. Okay, those are things I can actually find areas of using my geometry formulas. And the third method, we haven't learned yet, but we will. This is called the fundamental theorem of calculus. Okay, and this is going to be one of the main results from our class. We'll cover this in the next section, section 5.3. But this theorem, this will connect. It will connect areas with antiderivatives. So somehow we'll be able to find an area under a graph using antiderivatives. And that, I think, is amazing. Because sort of ahead of time, there's no real reason we might think that those are connected things, finding an area, computing an antiderivative, but there is going to be a great connection between these that will make the problem of finding an area under a graph way simpler, and we'll see that in section 5.3. So in terms of our goals for this section, we finished goal 4. Computing a definite integral, thinking of it as a signed area. We've been able to do that when our graph is simple, linear and circular paths, by just finding the area using geometry.